Okay, I guess let's get started. Let's see, is this working? Yes. Um, so I guess last time we have talked about unsupervised learning, and today we're going to continue with unsupervised learning. So I guess and first we're going to continue with the moment method, and here we're going to talk about higher order moment. And then next, we're going to talk about something called clustering or spectral clustering in more technical words. So these are different type of unsupervised learning algorithms. So I guess just to continue with what we had last time. Last time we ended up at this mixture of Gaussians. The setup was that you have some x which is sampled from a mixture of k Gaussians with mean mu I and covariance identity. And so at last time, I think at the beginning we talked about case 2, we have mixture of two Gaussians, and in that special case you can just take the second moment of the Gaussian to recover the mu i's. And then we moved on to talk about case bigger than 2, and in that case we have argued that if you take the second mixture, right, if you take the second moment, then this is something like 1 over k times sum of mu I transpose, and this is not enough to recover mu i's, because given this second moment, you still cannot identify the mu i's precisely, because there are multiple mu i's that can have the same second moment. So that motivates us to consider the third moment. So the third moment is, as we discussed, is the expectation of x tensor x tensor x. So this is a third order tensor in dimension d by d by d. And let's compute what's the third moment, and with the hope that the third moment will tell us enough about mu i's so that we can recover mu i's from the third moment. And that's indeed the case. So what we do here is the following. So we compute the third moment, and I guess the initial step is always the same, because you have a mixture of k clusters. So what you do is you have 1 over k times the sum of the moment conditioned on each of the cluster I, where I is the cluster ID. And now the question becomes that if you have a Gaussian drawn from if you have an x drawn from Gaussian, then what's the third moment? What's the expectation of third moment, right? So what is this expectation of x tensor x conditioned on I? So so let's do some kind of like a simplification, just to, this is an abstraction in some sense, so that we can make the notation simpler. So suppose Z is from some Gaussian with mean, let's call it A, just to distinguish it from the mean A and covariance identity. Then the question is, what is, you have this lemma. I guess the condition is this, and then our question is, what is the expectation of Z tensor Z tensor Z? And the claim is that this is pretty much equals to A tensor A tensor A. But with some caveat, there's some other terms which are something like this. Let me write it down and explain. So this is L from 1 to D, expectation of X tensor EL tensor EL plus D expectation EL tensor expectation X. So this is a formula. Oh, sorry, my bad. This is not X, this is Z. There's no X in this lemma. We already changed our notation to Z. So note that expectation of z is really literally a. So basically, you already have a formula that expresses the third moment of z into a function of a, right? That makes sense because everything a decides everything. So everything at the end of the day should be a function of a, right? So the reason why we still use ez in this formula is because we want to implicitly say that this is something, there's something that is about the first moment. So maybe the more important thing is that this means that you can compute. So we can compute a tensor A from linear combinations, in some sense linear combinations of the third moment and the first moment. Why it's useful to get this? I think that will be clearer. Why it's useful to get a tensor A. It's useful. We'll see it in a moment. But this lemma tells you that if you know the first moment and third moment, you can get a tensor A. Sorry, I keep messing up with the letter here. So here is the Z. Okay, so and let's see. I think any questions so far? I guess it's not exactly clear why this lemma is useful, at the current point. I guess the main point is that you can compute out what the third moment when Z is just a Gaussian. And I think the proof, I'm going to show the proof. I think the proof is nothing super interesting, but it tells you how to do this kind of the derivations for the moment. And once you see it once, then all the others becomes kind of trivial. So how do you compute the third moment? So what you do is you do it for every entry. So you say you look at the ijk entry of this thing, then this is just expectation zi, zj, zk, where zi denotes the coordinates, the ith coordinate. And I think there's something, sorry for the note takers, I think I changed my notation to v here, just to be consistent. I mean, my bad. Change this to v. It's just a generic variable. It's just somehow later I use v, so let's change this to v. So, so what we do is that we just, to compute this moment, we just, in some sense, do this in a brute force way, right? So, what is zi, zj, zk? You can write zi be vi plus some cos I. And cj can be vj plus cos cj, and zk will vk plus cos ck. This is, we're using the fact that z as a vector is equals to v plus some cos c, where cos c is from spherical Gaussian. That's my definition of cos c in some sense. Cos c is equals to z minus v, and which has spherical Gaussian distribution. And then you can, and v, by the way, vi is the ith coordinate, just to be clear. So, and then we can expand this. So there are 8 terms in this product. So what are them? So one of the terms is vi, vj, vk. That's easy. V is deterministic because c is random, right? And some of the terms will look like expectation vi, vj, cos ck. One of the terms is this. And another term is expectation vi, vk, cos cj, and plus expectation vj, vk, cos ci. And these terms will be equals to 0 because the expectation of cos c is 0 and v is a deterministic quantity, so that's why they're going to be 0. And then we have the other 3 terms that looks like expectation vi cos cj cos ck plus expectation vj cos ci cos ck plus expectation vk cos ci cos cj. So these terms is a little bit different. Let me deal with it in a moment. And the last type of term is the product of the 3 cos c's. So how do we deal with the rest of the four terms? So the thing is that if you look at the expectation, cos I cos k, this is equals to what? This is equals to 0 if I is not equals to k. Because if it's equal to I is not equals to k, cos I and cos k are two independent random variables, and you can factorize it to get expectation cos I and cos k. They're both 0, so you get 0. And this is 1 if I is equals to k. Because, okay, maybe let's have more steps. So this is equals to expectation cos I squared, which is equals to 1 if I is equals to k. So in summary, expectation of cos I cos k is equals to indicator that I is equals to k. And you can also try to deal with cos I cos j cos k. And here you can still try to do the same thing, like try to divide it into different cases, whether I, j, k are all the same, or maybe both two of the I and j's are the same and k is different. There are a few cases. And actually, if you enumerate all of those cases, it turns out that it's always 0, like regardless of the choice of I, j, k. But for different reasons, right? For example, when I, j, k are all the same, then this is the third power of cos I. So it's equals to expectation cos I cubed. And that's 0 because Gaussian, the third moment of Gaussian is 0. And when I is equals to j and but not equals to k, you can do another different calculation. But generally, you can do all of calculations, and they all equal to 0. In some sense, I think the fundamental reason is that as long as you have as long as you have an odd degree polynomial, odd degree monomial of this cos i's, it doesn't matter. Like it's always going to be 0. The expectation is always going to be 0. So these are all, in some sense, elementary calculations. And then if you use this, then you can continue here. You can get this is expect equals to vi, vj, vk plus vi times the indicator j is equals to k plus vj indicator I is equals to k plus vk indicator I is equals to j. And this is pretty much completes the proof. So then you just have to rewrite this in a tensor form. So if you verify, I guess, how do you write it? I guess if you verify this equation, the target equation, entry by entry, then you see that this is actually exactly same. So this is VL tensor EL, sorry, V tensor. L plus. All right, so this is our target equation. This is what we got for every entry. So let's just verify these two, verify that they are the same thing. It's just a reorganization. So how do you verify that? It's kind of like if you take the ijk coordinates, you see that. So the question is what the ijk coordinate of this guy is, right? So V tensor EL tensor EL, the ijk coordinate is equals to, it always has a vi there because vi is always there. But the jk coordinate of this EL and EL depends on, so basically you have to, this is, the only possibility is that this is E. So the only possibility that, so basically this is like, I guess maybe one way to write this is that if you really do it, this is VI times EL, the j's coordinate of EL, and EL, the k's coordinate of EL, right? So, and in what case the j's coordinate of EL and k's coordinate of EL are both non-zero? The only case is that L is equals to J and L is equals to K. That's the only case that this can be non-zero. So that's why this is equals to VI times 1 when L is equals to J, L is equals to K. And the only way that this can happen is that J is equals to K, right? When J is equals to K. Otherwise, it's going to be 0. So that's how you verify it. I don't expect you to kind of verify it completely, on the fly. But in some sense, the exact formula doesn't matter that much either, right? You only need to have a formula that depends on the third moment of v, and also some like formula. Basically, you just need a formula for v. Okay. So any questions so far? So now let's see how we use it, right? So how we use it is the following. And you can kind of see what kind of things we exactly need. So now you look at the x, right? X is a mixture of Gaussians. Z was only a single Gaussian. And you use the single Gaussian thing on the single Gaussian as a building block to compute the moment of the mixture of Gaussians. And what you do is that, okay, when condition I becomes a Gaussian, and you apply the lemma, and you get 1 over k times sum over I from 1 to k, and then this is mu I tensor mu I, because mu I is taking the place of v. And then you have the additional three terms, mu I tensor EL, and EL tensor mu I tensor EL, plus EL tensor EL mu I. Okay, so parentheses. Okay, so basically the third moment of x is a function of mu i's. It's still a little bit messy. So what you do is you say, I'm going to get rid of all of these terms by using the first moment, the first and the moment of x, right? So what you do is that you first reorganize a little bit. You get this somewhat cleanly looking term, mu I tensor mu I, and then you switch the k with the two sums. For the rest of three terms, you get sum over L from 1 to D, 1 over k times sum over I from 1 to D mu I, tensor EL, and you have the two other terms, which I guess you can imagine what they look like. They just there are permutations, there are rotations of these terms in some sense, changing the order. And now this one becomes the first moment of x. So you get 1 over k. You get the same. Okay, this is I. Sorry, this is I. Plus something that depends on the first moment of x. Right. So what does this mean is that you can move these three things to the left-hand side. Right. So basically this means that we can compute this tensor from the third moment and the first moment. So that's basically our interface, right? Once you have this tensor, then the next step will be so we'll go from here. So from this thing, I guess let me write this. I think I should have introduced this to mu i's. So, and just for the notational purpose, so a to the tensor 3 is just a shorthand for a tensor A. So basically, what this this whole computation is saying is that now you can compute this expected sum of the third moment of mu I, and then you need to design algorithm to compute the mu i's from this. And if you can do this, question mark, then you're done. The whole thing is solved, because you can first use the moment to compute the third tensor for mu i's, and then you can run this algorithm. There are some, there are actually some cleaner ways to deal with this. We don't have to deal with this additional terms, to get. There are some other ways to get this exact third-order tensor just directly, cleaner way. But that requires a little bit other machinery. So that's why I'm kind of like only using this relatively brute force way to get the third-order tensor. But the point is that you can always get something like this. So now the problem becomes the so-called tensor decomposition problem. So abstractly speaking, this tensor decomposition problem is something like so abstractly, you have a sequence of vectors, a1 up to an. These are all in dimension ak, in a dimension d. So these are unknown. And what you're given is a vector that looks like this, right, from 1 to k. And then your goal is to reconstruct AIs. And you can also ask about this, for different orders of tensors, you can also ask the same question, so questions also for example, you can have some other rth order tensor for some r that is possibly bigger than 3. And it turns out that you can also get the fourth order kind of power from this moment method, right? If you take the fourth moment of the data, you can get AI to the tensor 4, with some rearrangement like what we have done. So basically, this is the kind of the kind of interfaces, right? You basically reduce the unspecified problem to this so-called tensor decomposition problem. And this tensor decomposition problem also has certain kind of like somewhat kind of like a let me also introduce some notions for this, right? So notation. So the rank of the tensor. So some basic notion. So the rank. So I guess let's say A tensor B tensor C is a rank 1 tensor. This is the definition of rank 1 tensor. And then the rank of a tensor K, tensor T, is the minimum K such that T can be written as a sum of K rank 1 tensors. Sometimes this is also called CP decomposition. So in some sense, like the reason why this is called decomposition is that you observe this sum of these rank 1 tensors. You want to decompose it into components, and each component is rank 1. So and this question is also sometimes called CP decomposition, because there are some other decompositions for tensor that could also be meaningful in other cases. But actually, it's also fun to just call it tensor decomposition, because this is the most popular decomposition for tensors. Okay, so now I guess now it becomes a very modularized question. It's an algorithmic question, right? How do you figure out the components from given a low rank tensor? How do you figure out the low rank components? So I'm going to what I'm going to do is that I'm going to basically list some of the existing results, but not really talking about details, because this is actually what happens, in this area. I think this area becomes kind of like very popular around 2013, 2012. And the very beginning, I think a few papers kind of lay out the framework for this kind of whole thing, right? So how do you compute the moment? How do you convert it into tensor decomposition problem? And then those papers provide some somewhat easy tensor decomposition problem, or they actually invoke some of the existing tensor decomposition problem. And that's the early papers. And then this field, somewhat kind of like because you have this question becomes two parts, right? One part is about how do you do the moment, right? How do you turn the moment into a tensor? And then the second part is how do you decompose the tensor? So people have, there are a lot of papers, involving some of my works as well, but there are actually a lot of works that tries to understand how do you decompose all different kind of tensors, like under what conditions you can decompose. So what I'm going to do is I'm going to list a few conditions that you can decompose these tensors, computationally efficiently, and those conditions you will turn into a condition for the upstream problem. For example, in the mixture of Gaussian problem, you're going to have some conditions. So just to set up the kind of the basis. Let me see where I wrote this. Somehow I didn't write this. So maybe the number 0 is that in the most general case, or in the worst case, in the more TCS language, right? So you call it worst case, or in the most general case, this problem is not solvable. So finding the AIs are computationally hard. Actually, there are several layers here as well. If you want to discuss the details, in the very worst case, actually the AIs are not unique. You don't have a unique decomposition. And when the decomposition is unique, there are also cases where the decomposition is unique, but you cannot find them in a computationally efficient way. I think there's a question. So just to get to the version, like if you first start out with that, so if you take 3, you replace 3 to be 2, then it's pretty much like symmetric. This here is symmetric, but you can also make it asymmetric. But yes, you are right. It's basically linear algebraic stuff like FD. And this is a very good question. So I think, in some sense, as you will see, like in some of discussions below, like in some aspect, the tensor decomposition is kind of close to matrix decomposition, but there is one fundamental difference. So that fundamental difference is what enables that makes this kind of tools powerful, but also challenging. Like it's powerful in the sense that it's fundamentally powerful because because here there's no rotational invariant. I guess this no rotational invariance also you have to interpret in a careful way. So what I mean is that sum of AI tensor 3 is not the same as sum of rotation of AI tensor 3. However, this is true for matrices. So if you have sum of AI transpose, this is the same as sum of R times AI. R is a rotation matrices. I guess it depends on how you rotate it. My bad. I think this. How do I say this? I probably shouldn't say this on the fly without thinking about what's the best way to. I guess technically I should rotate on the right. So maybe let me not make it precise, but I think maybe one thing to realize is that if you have matrices, you have A times A transpose, something like this, which is kind of like a sum of AI transpose if you put all the AIs as columns of capital A. So then this is equals to A times R A transpose if R is a rotation matrix. And you just cannot do this, for the tensors that often. So but what happens here is that if you have AI and you permute the indices to AI primes, right, where AI primes are just permutations of AI, then this resulting sum, the third tensor, is still the same. So you only have rotation symmetry, but no. You only have permutation symmetry, but no rotation symmetry. And this is actually make it somewhat powerful because in many cases this is the case. Like for mixture of Gaussians, you can permute all the centers, and that's still the same Gaussian. but you cannot rotate the coordinate systems to make it the same. You cannot rotate at least you cannot take linear combinations of the centers to still maintain the same mixture of Gaussian. And I think this also applies to neural networks. I think for neural networks, you have the permutation symmetry, where you can permute the neurons in intermediate layers and also the associated edges, and you can still maintain the functionality of the neural network exactly the same. But you cannot do arbitrary kind of rotations in it because you have the nonlinearity with the activations. So yeah, but I guess this part is supposed to be somewhat abstract because once if you see a lot of math, then you kind of probably understand this a little more better. But anyway, so there's some fundamental differences between this and linear algebra. So that's why tensor decomposition becomes difficult, especially in the worst case. Okay, going back to the list of questions. So as I said, the starting point is in the general case you cannot hope to do anything, but there are many cases where you can do something. So the easiest case is the orthogonal case. So orthogonal case means that if A1 up to AK are orthogonal, so and in this case actually this is the closest to the eigenvector case, right? This is so here you can say that then AI is actually the global, each of AI is the global minimizer. There are multiple global minimizers, so that's why each of them is a global maximizer actually, of this objective function where you maximize the L2 norm, maximize this tensor paid by a rank-1 tensor. So I guess if you're not familiar with the notation, then what I really mean is that you take this sum of Tijk times xi, xj, xk. So this is the extension of the quadratic form for matrices, right? So suppose you have matrix, then this is the quadratic form. And for tensor, this is this tensor form. And so eigenvectors can be defined in this way, if you change the tensor to the matrix, because eigenvector is what maximizing the quadratic form for the matrix. So in some sense, in this sense, the components are some kind of like eigenvector. And then you can find this. So this is an interesting property. So this is saying that AI is kind of like eigenvectors of T. And also we can find it. It's not trivial to find it, but we can find AIs in polynomial time. And actually, the way to find it is that you try to solve this optimization. At least one way to find it is that you try to solve this optimization problem by grading this set. So that's one case. And another case is that, more general case, that you can have the independent case. So it turns out that if A1 up to AK are linearly independent, then this is also a good case. You can find this in polynomial time. I think the algorithm is called Jenrich algorithm. I'm not going to describe all of this algorithm just because they will take too much time. And in some sense, these are things that you can, as long as you have some kind of like basic knowledge, you can search over the literature, and there are many papers about this kind of thing. But these are, 1 and 2 are both about so-called under-complete case. 1 and 2 are the so-called under-complete case, which just really means that K, the number of components, is less than D. You can see that number 1, number 2 can only happen when K is less than D, because if K is bigger than D, there's no way that A1 up to AN are linearly independent. It's because your number of components is bigger than the dimension, so they cannot be linearly independent. But actually, you can also do this for over-complete case. Over-complete cases are still possible. In certain cases. So there are several different ways to deal with over complete case, which means k is bigger than d. So the first one is that you can look at higher order tensors. So you can say that suppose A1 tensor 2 up to AK tensor 2 are independent. This is a much relaxed condition than A1 up to AK are linear independent, because now you have higher dimension. So now this only requires, k needs to less than d squared, right? Less than d squared to make this possible to happen. And suppose this is true, then you can just replace AI by AI tensors 2. So you can recover AI from the 6th order tensor. So you recover it from AI tensor to power 2 to the tensor power 3, I from 1 to k, and which is the same as the 6th order tensor. And how do you do it? You just invoke the 3rd order tensor on AI to the power 2. And then after you get AI to the power 2, you can get AI by just taking the square root. So this relaxes the restriction on the k. But somehow with the cost of estimating 6th moment, because how do you get this? This is a thing with in r to d to the 6th, so you have to somehow do something with the 6th moment, and it will be less sample efficient. And another slightly clever way to do this is that you can do 4th order tensor with the same condition. So you say that 4th order generic tensor. And what does generic tensor really mean? It means that you exclude excluding algebraic set of measure 0. So you exclude a small set of, a measure 0 set of tensors, and except those kind of tensors, you can do this. And this is saying that when k is less than d squared, you can recover AI from the 4th tensor. Right. So before, if you do the trivial reduction, you get the third. You need to use the 6th order tensor, but now you only have to use the 4th order tensor, and this algorithm is called FUBI. And you can also have a robust version of this. This algorithm by itself is not robust. You can also have robust versions of this. I guess let me not write down the references. I'll add the references later. I guess if you just if I could just get the initials, I think these are some references like this, where you can get a robust version of these algorithms. And if you want to be more ambitious, right? So you want to say that I want to even deal with 3rd order tensor, then what you can do is you can say you can have random tensors. And by random, it means that if you assume AIs are randomly generated. Right, for example, unit vectors. I guess whether it's unit vectors is not that important, but for convenience, let's say they're all unit vectors and they're all randomly distributed on the unit sphere. And then for even 3rd order tensor, k can be as large as d to 1.5. So you can handle over complete case even with 3rd order tensor. And there are some references here, which I guess I'll add it to the notes eventually. Okay, cool. So this is just a very quick list, kind of probably a little boring list of like references. But I guess you see the rough idea, right? So you can, for various conditions for the component AIs, you can have various kind of algorithms and different results, right? So typically, if you have more restrictions on AIs, you get stronger results, right? So the strongest one would be you assume they are random, then you can get you can even decompose over complete tensors when the order is only 3. But if you don't have that strong assumptions, you have to go with the 4th order tensor or even 6th order tensor if you don't use the right algorithm. So this is basically what's going on in this area, and you can see there are many papers that deal with different kind of like setups. So I will add some references to the lecture notes, but generally this is something you can kind of search on internet. And there are just before we conclude this part, there are other latent variables that can be done. By moment method or method of moment, using the same strategy where you first compute a moment, you turn it into a tensor decomposition problem. So you can do the so-called ICA, independent component analysis. You can do the hidden Markov models, and you can also do topic models. I think there are even more than this, and I'm just listing a few that are most prominent. So these are all latent variable models for unsupervised learning, and you can, for each of this, you can try to compute certain kind of moments and rearrange your moments so that you get a tensor, and then you decompose the tensor to construct the true parameters. Any questions so far?
When you get some, say, for example, the third order tensor, and so we want to estimate based on the data.
Right.
And I guess it would be more general kind of based on complete tensor.
It's more.
And then, so how can we use these different, say, 1K beta log? We want to kind of match the data with these calls.
I think let me maybe I didn't let me try to answer, and then you can clarify if I didn't answer the question. So I guess the flow is something like you first start with the data, you compute some tensor, maybe this, or maybe false order, maybe I say 4 here, and you of course you cannot compute this exactly. You compute this approximately. You have some error in estimating this false moment. And you know that if you don't have any error, then this will be something like sum of AI to the tensor 4, I from 1 to k. And then you decompose. You get AIs. And I guess, how does the dependency kind of, so where, like, I guess one thing is whether it's over complete or under complete, right? So why does that matter? That matters because this k is, what is k? In the mix of Gaussian, k is number of mixtures. So if you can handle over complete tensor decomposition, that means that for the original problem, you can handle more than d mixtures, right? Your number of mixtures you can handle is more than dimension. And if you can only do under complete tensors, then your number of mixtures has to be less than dimension. That's why people care about over complete tensors.
My question is, when you sum and approximates the expectation well, so like the decrease, so with more and more k, with larger k, you do that.
With larger k, the k here is something fixed. It's not about, okay. So I guess there's another thing, which is k is the something is the number of mixtures in your data is something fixed considered, right? So what is, I guess maybe what you're asking is this, right? Is this empirical thing, right? So the real thing is that you work on this, and then you say this is approximately equals to the sum of AI to the tensor 4, and then you decompose that approximate version. So you also need your algorithm, your decomposition algorithm, to be robust to some errors, right? Because you don't know exactly this thing, this low rank tensor exactly. You only know approximate version of it. I'm not answering the question. Go ahead. Maybe I'm not answering the right question.
Right.
Right.
This is the
Right. Low. You can think of tensor decomposition as a low rank approximation for the tensors. Yes.
So E theorem does not apply to them. So E theorem is only apply as approximation instead of.
So all of these theorems so far I listed, they all work for approximate version, even though I didn't really talk about the approximate version yet. Like I didn't talk about the approximation explicitly, right? So in some sense, the kind of the first order bit is that even you don't have any approximation, you get exactly a low rank tensor. You have to be able to decompose it. That's not trivial, right? So for matrices, it's trivial because you just take SVD. But for tensors, it's not trivial. So that's why the first order bit is to say, I get exact low rank tensor, I can decompose it. And then the second question is the so-called robustness, which means that you get approximately low rank tensor. How do you decompose it? I think all of these algorithms, I think, are robust. There are some robust versions of them. So, and typically, if you don't care about the optimal sample efficiency, then they're all robust just for trivial reasons. But if you really care about exactly how many samples and how robust they are, it becomes a little tricky because you have to talk about sample efficiency, like how does the concentration work, so on and so forth. Right. Yeah, you can kind of think of the AIs as the largest eigenvectors. Yes. You can roughly think of like that, yes. Okay, sounds good. Okay, cool. Okay, sounds good. So I guess, okay, cool. So then I'm gonna move on to the last subtopic, in this course. I guess it's still about unsupervised learning, but it's about slightly different type of unsupervised learning, which is more like clustering. And you can see that we are still doing spectral methods. We're still doing some kind of spectral decomposition, but it's decomposing in a slightly different way. Like I guess you'll see once I formulate the problem, and then you can see that before, when you do tensor method, you are building some pairwise information between the coordinates, or three-wise information between the coordinates of the data, right? So here, from now on, I'm going to talk about a different type of approach where you build pairwise information between the data points, and then you do something on top of that. So I guess I'll specify more clearly. So this is spectral clustering. So I'm going to discuss actually a bunch of different algorithm or setups, under this broad framework. This kind of whole spectral clustering kind of framework, I think, is proposed by Shi and Malik around 2000. I think also Andrew In, Mike Jordan, and Weiss in 2001. Maybe this is 2001, this is 2000. I will have the references in the lecture notes. So it has been like 20 years old. So I'm going to kind of discuss a bunch of like classical things about this, and also next lecture I'm going to talk about one of my own work, which kind of built on top of this to get it to a deep learning case. So to extend it to the deep learning case. So the general idea is that suppose you have, so we are given n data points. Let's call them x1 up to xn. And let's say we are given, for the moment, let's say we are given a similarity matrix. And don't ask me how to get this. Let's just assume that we have a similarity matrix G, which is of dimension n by n. Actually, it's going to be a problem, to construct this similarity matrix to some extent. But for the moment, let's say we have this. In some cases, we do have this similarity matrix, and this G, where each of these entries of this matrix is doing some similarity, is capturing a similarity between two data points, xi and xj. here, you can interpret this as similarity or something like some, or just generally some matrix that captures some relationship between data points. I think it's reasonable to think of them as similarity. So, and the larger, the more similar, I say. But this is not that important. So I guess you can see that this is what I call the pairwise information between data points, but not pairwise information between the coordinates. Actually, if you do, in certain cases, they are kind of the same, but in some other cases, they are not the same. So for example, one example could be that you have xi's are images, and then rho xi, xj measures the semantic similarity of the two images. How do you get this? I think it's a little bit kind of tricky because typically you cannot just take the L2 norm to measure the semantic similarity. Because there could be two images that looks pretty different, but they're semantically similar. But for the moment, let's assume we are given such a matrix, such a similarity matrix. Example 2, which is probably more kind of like classical usage of this kind of like models. So where you can say, think of xi's are users of social network. And rho of xi, xj is equals to 1 if they are friends. Like on Facebook, let's say. So and when they are friends, it means that they share some kind of like similarities, maybe similarity in jobs or interests or some other things, right? So you can think of this as a similarity measure between two users. And eventually you want to classify, in this case, you eventually want to classify the users into groups, right? So you want to say, I can detect hidden communities between users from this unlabeled graph. And so basically the goal is to do some clustering, do some kind of clustering. I guess maybe I should just clustering. Clustering the data points. I guess in the social network example, maybe you have like all of these users, where you have, let's say, so many users, and there's some friendship relationship between them, something like this maybe. And then what you want to do is you want to detect some so-called hidden community. So for example, you can say this is a cluster, this is another cluster, and maybe this cluster corresponds to people at Stanford, and this cluster corresponds to people at Berkeley. And right, so of course, between Stanford students, you have more connections, and between Berkeley students, you have more connections, and there are some connections across the groups, and so forth. And in this case, and also, for example, for this example 2, you can think of this also G as a graph. I think even in general case, you can view G as a graph, but it will be a weighted graph. Here, G in this social network case, G is binary because Gij is binary, so you can view G as a graph, and Gij is an edge. And your goal is to kind of partition. There are many ways to say what your goal is, right? So you can say you are clustering the data points, or you can say you are partitioning the graph into different parts, so that each part has more connections. Within each part, you have more connections compared to across different parts. So, so in some sense, this is you can now view it as partitioning the graph into kind of like components that are separated from each other, to some extent. There's no way you can completely decompose into completely disjoint parts, but you can somewhat kind of decompose them. kind of like partition the graph into more or less disjoint parts. And so this is the kind of the general type of setup. I'm going to kind of like discuss probably one or two instantiations about this. So I guess the general theme is that is the following. So this is I feel like this is a pretty deep kind of like observation in math. And the general kind of way to think about to say this is that eigen decomposition of this graph G really relates a lot to the graph partitioning. So eigen decomposition of this adjacency matrix G, here by G I really mean the adjacency matrix, relate to very well to the graph partitioning problem. So you see that, in all of the examples I'm going to give, the main approach is to do some eigen decomposition. And actually, sometimes it's not eigen decomposition of G, it's eigen decomposition of some transformation of G. But the key point is that eigen decomposition seems to relate so much to partitioning and clustering. And it's not that obvious, right? Eigen decomposition is a very linear algebraic thing, and graph partitioning is a very combinatorial thing. And this is why it's kind of like useful, because when you deal with combinatorial stuff, right? Typically, the way, at least my kind of, I'm not really a combinatorics person, but my way to think about it is that many combinatorial stuff, once you can relate it to algebraic or linear algebraic or other kind of like polynomials, then you get exposed to a different type of tools, and you can do a lot more things. Sometimes a lot more things than you expected. So this is the general thing, and we are going to see probably two or three examples to see why this is the case. So now I'm going to do something more concrete. So this is called stochastic block model. This is a very concrete setup where you can do math and you can say what I mean. You can instantiate what I mean clearly. So this stochastic block model, I think this is abbreviated to SBM. And so G is assumed to be generated randomly from two. Sometimes it could be more, but I'm doing only two groups, two hidden communities or groups. So the setting would be something like you have n vertices or n users, and you assume that there are two hidden groups, S and S bar. And this is a partition, meaning S and S bar are disjoint. And then you assume that if you are from two users are from the same hidden community, then they are more likely to be connected via an edge. So if I and J are both from S, or I and J are both from S bar, then the probability Gij is 1 with probability P, and 0 with probability 1 minus P. And then if I and J, and otherwise, if I and J are from different otherwise, which means that they are from different community, then Gij is 1 with probability Q and 0 with probability 1 minus Q. And here, importantly, P is much larger than Q. Maybe let's say much larger for the moment. How much larger, we'll quantify it in a moment. But you need P to be larger than Q. I guess maybe I just read larger, but not much larger. So basically, from the same hidden group, you have a higher chance to be connected by an edge compared to from a different hidden group. I guess, if you draw this, I guess, I don't know how to draw something, a random graph, but I think you can think of there is an S and there is an S bar. some edges, and then if P is something like probably close to 1, then you're going to have something like this. Within the group, you have high probability to connect each other, and across the group, you have some sparse edges, maybe just some random edges. Okay, so and now the goal becomes, so the goal is to recover S and S bar. If you recover S, you can recover S bar from the graph G. Right. So this is a well-defined data generation model, and you want to discover the hidden groups, right? You want to do the clustering. And our approach is gonna be eigen decomposition. So maybe before talking about eigen decomposition, for some extreme cases, you don't have to do eigen decomposition, right? So suppose, let's just do some kind of like somewhat trivial warm up, right? So suppose P is 0.5 and Q is 0. Then you don't have to do any kind of like, I think almost likely you don't have to do anything because you're going to see two disconnected parts, right? So if P is 0.5 and Q is 0, you basically have some S and S bar, and you have some edges, not complete connections. You have some edges here. And then there's a clear two subgraphs. You can just basically kind of like, for example, you can say I start from this, I look at all my neighbors, and I put them all in S, and then, because if you see the edge, you know that they are from the same group, right? Because if they're not from the same group, you have 0 chance to see an edge, right? So basically, you just need to see all the points you can reach from this a single point, and you got all of these 3 points, and then you declare that to be S. And the same thing you can do it for the other side. You can do some kind of like you can just try to. Does it make sense? I saw some confusions. I don't know. Like basically, the algorithm I'm going to do is the following. I start with a node, and I see what this node can reach to, and I put it into my set, and then I do this repeatedly to see what other nodes I can reach to, until at some point I reach the boundary. I reach a closure. I cannot reach any new nodes, and declare this to be, and then I declare this to be S. So, and the rest of them I declare to be S bar. That would work pretty reasonably well for P is 0.5 and Q is 0, and that's just because first of all, you don't have any false positive, because like all the nodes you discover should belongs to the same group, because and second, I think you can also try to show that you can find all the nodes, because if somebody is in your same group, it should connect to someone, right? And then someone or like this is the so-called small world kind of phenomenon, right? Like if this other user is from the same group, they should be connected with you by some paths. So anyway, so this is but you can see, even for me to convince you this algorithm is working for P is 0.5 and Q is 0, it's not that trivial, right? You have to do something, right? And this is a combinatorial algorithm. And what we are going to do is that we're going to do a more kind of like linear algebraic type of algorithm, and you can see everything becomes kind of even clearer, and this is a more powerful algorithm, and you don't need those combinatorial reasoning. So what do we do? So we basically just do eigen decomposition, and as a warm up, what we're going to do is that we're going to do eigen decomposition. How do I simplify eigen decomposition? What's the right acronym for eigen decomposition? Eigen decomposition for G bar, which is the expectation of G. So clearly, so what is G bar? G bar is the expectation of G. So you have a weight, and the weight is the expectation of you just take expectation of Gij. So clearly you don't have this G bar, but let's just for the starters, let's look at this expected version, right? So, and what is expectation? What is this G bar Ij? This is going to be equals to P if I and J from the same class, from the same community, and equals to Q otherwise. So that means that basically if you look at this G bar, So suppose this is the indices for S, this is the indices for S bar, this is the indices for S, and this is for S bar. So when you have both I and J from S, you get P. So you get P like this. And here you get Q. Right, so this is G bar. So, and my claim is that in this case, suppose you have the access to G bar. So the top eigenvector of G bar is the all-one vector. And the second eigenvector of G bar is interesting. Is this vector where you have ones on the coordinate in S and -1 on the coordinate in S bar. So basically, if you got the second eigenvector of G bar, you solve the problem because you can read off the community membership from this eigenvector. That's the claim. Okay, so it sounds a little bit kind of interesting, right? Like the proof, I guess, what's the intuition here? So I guess the intuition probably partly comes from the proof. So let's first do number one. Number one is kind of like almost always true for any cases. It doesn't even have to be such a special G bar. So what you do is you just say you look at G times all-one vector. And what is G times all-one vector? Basically, you multiply G with all-one vector here, right? Something like this. And you multiply it. Basically, you are just looking at the row sum. Looking at the sum of the entries in each of the rows, right? That's what's G times 1, right? So what's the sum of the entries of each of the rows? The sum of the first row is something like P times n over 2 plus Q times n over 2 because there are n over 2 entries with P and n over 2 entries with value Q. And every row has the same thing. It's just a. So this is equals to basically simplify this P plus Q over 2 times n times all-one vector. So and you can kind of see that 1 is the top eigenvector. Actually, even for more general kind of graphs or weighted graphs. So for any matrix with fixed row sum, or for any graph with so-called uniform degree, right? The degree of a graph is really literally the row sum of the adjacency matrix, right? So how many edges you have connecting to each of the node vertices, that's basically the row sum. So if all the degree of our vertices, all the vertices is the same, that means the row sum of the adjacency matrix is constant, and that means that all-one vector is the top eigenvector. So this is a very interesting fact. So basically, top eigenvector doesn't really tell you much. You have to go to the second eigenvector to see the interesting things. So now let's look at the second eigenvector. So what I'm going to do is there are many ways to evaluate whether this. Let's call this vector U. There are many ways to verify U is an eigenvector, right? You can directly multiply it and see what's the eigenvalue. I think probably the most intuitive way to think about it is the following. So let's look at G bar. Let's subtract from G bar a background thing. Which one you were talking about? Sorry. Oh, sure. Yeah, but the cardinality of S is n over 2. Oh, I guess, sorry, I didn't assume that. My bad. I didn't assume that this is an equal partition. I should assume that. So this is also for simplicity. Assume S is n over 2, S bar is n over 2. If they're not equally weighted, I think you have to do a little bit other things to deal with it. Not super important, but yeah. So if the S and S bar are not exactly the same, I think all1 vector is not the eigenvector anymore. So you have to reweight. You have to kind of like massage this matrix G a little bit to make it still true. But that we'll get to that in a moment. In next lecture, I guess. So, but so far, okay. So let's assume S and S bar are balanced. And now, how do we see the second eigenvector is this vector U that we want to look at? We're looking for, right? So what my way to think about it is that you subtract G bar, you subtract from G bar this background matrix, 1, 1 transpose times Q. So basically, you subtract Q from this every entry of this matrix. 1, 1 transpose times Q is really just a matrix with all entries being Q. And then what's left is this matrix, let's call it, let's say R is equals to P minus Q, you get R, something like this. So, right, so this is S bar, S bar. Right, and here we have 0. Okay, so now you can see that this matrix becomes nice because it's a block diagonal matrix. So for this matrix, if you want to verify, maybe let's call this matrix G prime. So we can verify G prime times U is equals to U. And how do you verify it is equal to multiply of U? How do you verify this? This is just because you can do this for the two blocks separately, right? So this is really just something like R times 1 minus 1 minus 1. All right, so when you do these two things separately, and basically you get R times n over 2 for the first n over 2 coordinates, and you get minus R times n over 2 for the second set of coordinates. So this is R times n over 2 times U itself. So, and also, U is orthogonal to all1 vector. Just because half of them are positive, half of them negative, so you take the inner product, it becomes 0. So that's why if you even look at G bar times U, this is equals to G prime times U, because the background you subtract off is orthogonal to U. So that's why this is equals to R times n over 2 times U, which is P minus Q over 2 times N times U. Okay, so that's why U has eigenvalue P minus Q over 2 times N. So this is so I think the main point is that after you subtract off this background thing, then this G prime is block diagonal. And this means that the eigenvectors aligns with the blocks. I think this is the kind of the fundamental things that we are looking for. Maybe to generalize this to make it looks a little bit kind of like more convincing. So suppose you have a matrix A which looks like this. Suppose you have some entries 1, 1, 1 here in this block, and you have a lot of ones, and you have a lot of ones here. Suppose you have 3 blocks now instead of 2 blocks. Then because you have block diagonals, right? So you know that for every block you can do your own thing, right? So then if you look at the eigenvectors, you can see that this So I guess each of these three vectors are eigenvectors, because you can do each of the block separately, right? So I guess there's a so basically you can say that so you can say that I'm going to choose the all-one vector for the first block and then zero at all the other places. That's still eigenvector. Okay. So and then when you have this, then you have that if you have these three eigenvectors, then the rows, if you look at every row here, right? So this is 0, this is 0, this is 1, right? So this row gives the cluster ID of the vertex. So each row gives you the cluster ID of the vertex. So I think this is the fundamental intuition about why eigenvectors are useful for capturing the kind of like the clustering structure in the graph. It's just because in the extreme case, when you have extreme clustering, right? So every block, every subset of the, like in these three blocks or three subsets, they have like really just a strong inner connections and no any other cross groups connections. In that case, the eigenvectors is just strongly kind of aligns with strongly aligns with the block structure. So and here I think like and then but you see but it was complicated. What makes things a little bit more complicated is that you have some background, right? So you have some more things here and here, right? So some random entries, small entries, other places. Then it will change it will elevate the entire matrix a little bit, right? But it wouldn't change the eigenspace fundamentally. That's pretty much the intuition. Any questions?
So it seems like here you have this nice big block diagonal structure, but in general you have like some permutation of the rows and the columns.
Right.
You will have this nice structure.
Right.
So it seems like how would you?
Yeah, that's a great question. Actually, that's exactly why this is working, right? Because so the question is that what if you permute this, right? So if you permute it, it's kind of like you're permuting your eigenvector will permute accordingly. So suppose you have I'm not sure whether that makes sense. So for example, suppose you have you say you declare this part and this part to be the first block, right? And then this part and this part will be the second block. I think your eigenvectors will permute, like the coordinates of the eigenvector will permute accordingly, and that's why it's aligned with that's why the alignment is kind of maintained, and you can discover the hidden structure. Okay, so okay, sounds good. So I guess maybe another thing, I'm not sure whether this is a confusion for you. Like it could be a confusion, it could not. Like so here the eigenvectors, there's no negative values in this construction, right? But it's kind of like the reason is that the reason why I didn't have negative value is just because it makes it simpler. Because so for example, let's say even this matrix, this vector, this is also eigenvector because it's the sum of two eigenvectors, and all of these eigenvectors have the same eigenvalue. So any combination of the eigenvectors is still an eigenvector. That's how you get the negative values. So and there's something special about all one vectors, like because so here there's like in this example, in this A example, there's nothing special about all one vectors because there's no this background noise. But when you so what happens is that when you add a kind of a background noise to it, then the all one vectors becomes stands out. So here you have 3 eigenvectors that are equally same, but when you, and all 1 vectors is in the subspace of these 3 eigenvectors, right? So like all 1 vectors is indeed a linear combination of these 3 things. And when you add the background noise, the all 1 vector direction stands out, and then you are left with 2 other directions, which are still the same. And those 2 other directions will tell you the block structure. So maybe another way to think about this is if you have 2 blocks, suppose you have 2 blocks. So if you don't have any background noise, then the eigenvectors will be 1, 1, 1, 0, 0, 0. This will be the 2 eigenvectors. But then when you add a background, and you can represent these eigenvectors in 2 different ways, right? This is an eigenvector eigensystem. You could also write it like this. Just because you have different ways to represent a 2-dimensional subspace of eigenvectors. But when you add the background noise, then this one will stand out. So that's why you can only use this system to see it, but not here, because I'm not sure whether that makes sense. No. So basically, without adding the background noise, you have this direction, which is this 1, 1, 1, 0, 0, 0, and there's this direction, 0, 0, 0, 1, 1, 1. And also you can have this direction, which is the all 1 thing, and this direction, which is the 1, 1, 1, minus 1, minus 1, minus 1. So they're both so you have this 2 different set of coordinate systems. And when you add background noise, you're going to elevate, or you're going to increase the strength in this direction, but the subspace doesn't really change. Like this direction becomes the top eigenvector, and this becomes the second eigenvector. But fundamentally, nothing really changed that much. I hope this only clarifies this, not confuses. Okay, so I guess I'm running out of time. Let's see. So I guess I'll take two minutes to kind of give a quick overview, wrap up, and give a quick overview what we do next. So basically, you can also actually, if you really want, you can verify G is actually equals to P plus Q over 2 times 1 transpose plus P minus Q over 2 times 1 UU transpose. This is the eigen decomposition of this matrix. And okay, G bar. So next, what happens is we only have access. So in reality, we only have G. So what do we do? What we do is we just say the intuition is just that G is approximately equals to expectation of G in certain aspects. It's not true that every entry of G is close to every entry of expectation of G, right? Because if we take one entry, G is binary, and the expectation of G is P or Q. There's no way they are close. But this is in terms of the spectrum. So essentially, we want to show that essentially, even though we need a little trick to make this work nicely, essentially we want to show the operator norm between the difference between these two is small. Then, if even you use G to do the decomposition, so this means that decomposing G is similar to decomposing expectation of G. That's pretty much, and now you can see that the concentration inequality that we discussed in the early lectures in this course becomes useful. So concretely, what you do is the following. So you write G. You write G as G minus expectation G plus expectation G. Expectation G is just G bar. And so this is G minus expectation G plus P plus Q over 2, 1, 1 transpose plus P minus Q over 2, 1, 1 transpose. Sorry, UU transpose. Right, so you want to say that this part doesn't matter too much, right? Doesn't really change your eigenspectrum. It's to make it cleaner, what you can do is that you subtract this part, because U is something you want to discover. The top eigenvector is something you already know. So we probably shouldn't estimate the top eigenvector. You should just directly look for the second eigenvector. What you do is you move this to the left-hand side. So you get this P. You look at this matrix. This is something you know, because G is something you know. And then this matrix is equals to this plus P minus Q over 2. So you view this as a perturbation, right? And this is something you are really looking for. So basically, you start from the left-hand side, you take an eigen decomposition. So you do eigen decomposition of G minus P plus Q over 2, 1, 1 transpose, and you hope that the top eigenvector of this matrix is close to, and the hope is that top eigenvector is close to U. That's basically our goal. And how do you make sure that this is the true? The only thing, so it suffices to show this G minus EG in terms of the spectral norm is much smaller than the noise is much smaller than the signal in terms of the operator norm. And this so in some sense you need some robustness of eigen decomposition. I guess I didn't really discuss any of the existing theorems, but essentially if you have this, you can prove that eigenvectors of the sum of these two matrices is very similar to the eigenvector of one of these matrices. And this is called Davis-Cahan theorem. I guess I wouldn't have time to talk about all of this, but this intuitively it sounds makes sense, right? So if the noise is small enough in terms of the spectrum, the operator norm, then you get the signal. And how do you get this? I think we're going. How do you show this is true? I think I'm gonna discuss that in the beginning of the next lecture. It's essentially you just have to prove some concentration inequality using some of the tools we had in lecture 3 or 4 of this course. Okay, any questions?
When we got multiple clusters, will the noise also change the eigenvalues when there's a lot of clusters will set off?
So if you have more clusters, the noise will hurt the entire spectrum, right? So and it becomes a little more complicated. So first of all, if you have no noise, then you can still prove that the eigenvectors are enough for you to recover the blocks. But this robustness theorem will be a little bit tricky because now you have more eigenvectors, and the noise has an influence to each of them, and you have to control. You have to again control some noise to signal ratio using a little more advanced techniques. But essentially I think it's just really the mathematical part is a little bit more complicated, but fundamentally it's still doing the same thing.
Related question: is it sufficient to? My impression is when you added this noise, this eigenvector unit is going through current. The new second eigenvector, we want to show that it's close to U, and when I asked the top eigenvector of the new matrix is close to U. When we analyze the operator norm of G minus the expectation of G, that kind of feels like we're trying to balance how much all of the eigenvectors can do. Do we really need to do that, or is there a way we can sort of go around it and just sort of argue about how the top eigenvector?
Yeah, so I think that's a great question. I guess just to rephrase your question, you are saying that do we really need to say that G minus EG is small in all directions? Do you just have to say that G minus EG is only not matching up with the direction U? I think you do have to say, to some extent, G minus EG is small in all directions, because if G minus EG is very, very big in one direction, let's say, even that direction is completely orthogonal to you, let's say, then that direction will be a new top eigenvector, right? So because you're talking about the max, right? You're not, right? But I think like how do you exactly measure this? You know, there's still some room to negotiate, but you do have to, in some sense, say something about all directions of the noise. Okay, thanks. I can see you on Monday. Oh, Wednesday.